All right, so this is a sample exam question. This has a lot to do with the motor system that we talked about. This is the input and output. I'm going to redraw this just because, you know, I think I like drawing block diagrams. They're great. So the block diagrams, here's what we have: some input. I'm going to preserve this disturbance thing because the disturbance part of it is really disturbance rejection is the crux of control system stuff, and everybody glosses over that a lot. It kind of gets taken into account automatically. So this is the open loop system, right? So, but if somebody says to you, "Oh, I want you to design a control system to design a control system," wait a minute. I know what design a control system means. It means I'm going to use my magic control law. So I'm going to start with a proportional controller where this is the desired position. I'm going to subtract the actual position, and then I'm going to multiply by some gain. There. That's my closed loop controller. Now, um, you know, for this one, what I can do, um, what they're asking me to do is a 5% overshoot. So I'm going to say C, the generic second order response that tells you 5% overshoot corresponds to zeta equals 0.707. All right, so you can do that. We've talked about it. We did it. All that stuff. So sketch the response to a unit step input. Actually, we can do this part even before we even start because it says design it this way. I'm going to go and look at my generic response curves here. It's zeta equals 0.707. It's this one right here. And so I'm just going to redraw this down here, and it's going to look something like this, where the settling time, Ts, is equal to 4 over zeta omega n. I don't know what those are yet, but I also know that the peak time is equal to tau peak over omega n, 3.14 over omega n. Again, I don't know what omega n is just yet, but I can just draw. I can already draw the output because I'm designing it this way. I'm using the characteristics to make it do this. Time is a little bit of a different thing. All right, so let's see what the transfer function is. T of S. So the transfer function is the output over the input. It is in this case, it's x over x desired. We have a couple of different formulas for this. Now I'm going to emphasize this other one. It's the numerator of g times the denominator of h divided by the denominator of g times the denominator of h plus the numerator of g times the numerator of h. And if I plug all that in, that's going to be the numerator of g, kp times 20 over s squared plus 5 in the s, 5s plus kp times 20. So that's the transfer function. That's the closed loop transfer function. And you know what I can just do? I can just say that omega n squared and 2 zeta omega n are that. So I say omega n squared is equal to 20 kp. That means that omega n is equal to square root 20 kp. And then I'm going to say 2 zeta omega n is equal to 5. And so that means I can just plug in for that. I know what this is 2. This is a 0.707. And this is omega n is 20. Square root of 20 square root of kp is equal to 5. So I'm just going to square that. It turns out that this is 1 over the square root of 2. And then I can just say square root of 2 over the square root of 2. So this is just 2 times 20 times kp equals 25. Kp equals 25 over 2 times 20 equals 0.625. Doom. Okay, so now I've calculated out what that is. I can tell you anyway, without any too much, I can see T of S equals 0. The steady state gain is equal to 1, which is the output over the input. That means that the output is equal to the input. Yay! That's what we want, right? That's what we're trying to do. All right, so now what we have to do is, okay, wait a minute. There's this other thing here. So I'm going to go ahead and draw this D of S. I'm going to redraw this D of S. Comes into my system. There's a plus sign here. And there's a plus sign here. I kind of worry now that if I go back through my formulas, remember there was a plus and a minus there. I don't know what I have to do with that. Anyway, I'm just going to draw this first and then we'll deal with that. S squared plus 5S. And this is X. And then I'm going to follow X around. Okay, I'm just going to do it this way. I like to do it this way. Oops, that's not plus. This is minus. This is plus XD. So I have that summing junction there. I've written it a little bit different. X desired. I should make it X desired. Now I'm going to put in a KP. And I'm going to put in a 20. So this is the equivalent transfer function. And now what I'm going to do is I'm going to say, you know what? Let's just say, for now, I'm not going to worry about. So there's two inputs to the system, either XD or D. And right now, I'm not going to worry about this one. Forget about it. Forget about it. Okay. So now we're done with that. And now I'm going to have you go back and look. And so what I want to do is I want to take this minus sign and I'm going to pull some shenanigans and I'm going to transfer it all the way over to here. And now that is a minus sign. So now I can just use the regular formula. So I turned it back up. You know, it could be a plus sign. I'm just following that minus sign through rather than multiplying by -1 here. I'm just following it all the way through. So now I'm going to say, here's what T sub D of S is. TD of S is still the output over the input. That's always what the transfer function is. It's output over D of S. Should maybe write that X of S. And that's going to be the numerator of G times the denominator of H divided by the denominator of G times the denominator of H, which is just 1, plus the numerator of G times the numerator of H. Oh, numerator of H is 20 kp. Oh. And then what I'll notice here is that, by the way, same characteristic equation. That's important. They always are. If in one closed loop system, the characteristic equation is always the same. And now what I can do is I can say, oh, T sub D of S equals 0. T of D of S equals 0 is equal to 1 over 20 kp. So it says, like, what is the error for that? Like, it's hard to know what the error is, right? The error is it's 1 over 0.08. So if I put in a unit step input, it moves it by that much. So if I put in a unit step X D equals U of T and D of S equals U of S, U of T, I don't know how to do it anyway, then it's an 8%. Then it's an 8% error. So all this talk about error is a little bit wrong. But what we need to understand is that this moves it by 0.1. With that gain, it moves the disturbance will move my system by about 1/10. Wherever it is, it's going to move it by 0.1 of the unit step input disturbance. Okay. So that's one way of doing it. We don't even have to know anything about controls or anything to do it that way. We might as well try and do, why not? Why not? Why don't we use a little bit of controls here? Want to? Okay. Well, let's do it again and let's use a little bit of control system technology here. Control system technology here. I'm still going to put this in here. I'm still going to use 20. I'm still going to include the d. Again, I hate to throw away the d, although we throw it away all the time, but then we bring it back in later. 1 over s times s plus 5 x, right? So here's the thing. This is called, I'm going to do this. This is the open loop system. Everything in there is the open loop system. And, you know, one thing I might do, I might just write it that way. What the heck? You know, it turns out I could do this. I should probably do this. H of s equals 1. Let me say h of s equals the numerator of h over the denominator of h equals 1 over 1. Let me just make sure that we, and this is still the open loop system is what I've drawn here. And the reason it's the open loop system is because I've cut it right there. This, I call this input. There must be, should be a better name for that, but I don't know what it is exactly. And then what I'm going to do is I'm just going to write in here, okay, GH of S is equal to 20 over S squared plus 5. I kind of, you know, I've kind of 5S, oh, sure. I kind of obscured the fact, you know, when you do it this way, you can see that's S equals 0, that's S equals 5. This one, you can probably do it too, but you have to do at least a little bit of factoring to get that into some position. All right. Oh, in fact, let's make sure that I do this right. This GH is 20 over S plus 0, S plus 5. Okay? Those are the two open loop poles. Open loop poles. Oh, open loop poles. You know what I should do? I should look at what the closed loop system looks like here. Okay, I'm going to look at what the closed loop system. So I know the closed loop system. In generic terms, this is the closed loop system is going to be the T of S is equal to the feed forward over 1 plus the feed forward times the feed back. Right? Oh, let me do a couple of things here. So one again, if this is a closed loop control system, I'm going to put the closed loop controller in. XD plus minus. I'm going to put the closed loop controller in. That'll be fine. And then if I put the closed loop controller, a lot of times, so this is always ambiguous. Can I just absorb the KP into G of S, or do I explicitly pronounce it that way? People do it different ways. And so now what I'm going to do is I'm going to look at what the transfer function is. The transfer function is output over the input. That's always the transfer function. This is going to be x desired. Oh, that's going to be x over x desired in this case. And it's going to be KP. Oh, so we've got all that. But what this does is it tells me that the characteristic equation for my system is 1 plus KPGH equals 0. That's the characteristic equation. That's what that characteristic equation governs the dynamic response of my system. And since it governs the dynamic response of my system, I want to see what's going to happen here. And what I'm going to do is I'm going to draw a root locus for the open loop system because, why do I know? Because the root locus for the open loop system, the reason I'm drawing a root locus for the open loop system here is that I know that 1, 2, 3, 4, 5 minus 5. 1, 2, it's always hard to, the vertical ones, you almost always screw those up because your sense of proportionality is off in the up direction besides the side. This is the real and this is the imaginary. All right. And so what I'm going to do is I know that for the characteristic equation, because the way this works the way, if I want to, okay, so if I want to go through the whole steps of it, let's go through the whole steps of it. It says that T of S also equals the numerator of G times the denominator of H divided by denominator of G times the denominator of G times the denominator of H plus the numerator of G times the numerator of H, right? So we know that. And that means that the characteristic equation is the denominator of G times the denominator of H plus the numerator of G times the numerator of H. And so equals 0. And sometimes we want to write this. Sometimes they, they always want to put that KP in there. So let's just put it in. Sometimes some of them want to leave the KP out. Sometimes I'm just going to absorb the KP into the numerator of G. It's your call, your decision, however it works. But what we can see here is that when KP is 0, it starts at the open loop poles. When KP is infinity, this part goes away and it ends at the open loop 0. So let's draw where the open loop poles are. Here, this is S equals 0. Okay, good. Here's a pole at S equals -5. Okay, perfect. We can go through all the different rules that they have here. There's always a bunch of them. Let's do it with, I'm trying to think. Okay, the number of infinite asymptotes is equal to the number of poles minus the number of zeros. Number of finite poles minus the number of finite zeros, that's going to 1, 2, minus 0 equals 2. And so I don't have to go too far. There's a formula for it, but I've also passed out this thing. It says, oh, if there's only one infinite pole, it's there. If there's 2, it's this way. If there's 3, it divides the plane into 3 equal parts. If it's 4, it divides it into 4 equal parts. If it's 5, it divides it 5, 6, 7, 8, 9, 10. But you can keep going for as long as you want. All right. So one of the things that we might want to find out is what is so since we know this is the asymptotes, the theta asymptotes is plus or minus 90 degrees, we might want to find out where the intercept point is. And there is a formula for that. It's the sum of the poles minus the sum of the zeros divided by the number of poles minus the number of finite zeros. And so that's going to be the sum of the poles is going to be 0 plus, okay, this pole is -5. That's all there is, divided by 2, 2.5. Okay, so this is sigma asymptotes, sigma A. And because it's plus and minus 90 degrees, we can just draw this asymptote. Now, I'm drawing this asymptote on, up, and down pretty far here, because I want to emphasize to you, I already had you do this. You may remember that I had you do this. See homework 2 solution at blackbeard.com. That's not where it is. It's on the Blackboard thing, right? It's on the Blackboard thing. And in that one, I told you to do KP, and then I had R1 and R2. So I would write those down, and then 0, and then whatever those were in 0.1, and then whatever those were in 0.2, whatever those were. And what that did was when we did it, we could see that there were some roots. There were a pair of roots, and then there was another pair of roots, and it went up. And then they just kept going up this line eventually. And also on the homework solution, we could see that the disturbances, the disturbance part of it went away as KP got bigger and bigger. We saw that the last time we just did it here, right? Here's the disturbance one. As long as the KP gets bigger, the effect of the disturbance gets smaller and smaller. Now, it is true that as we move up this line here, our oscillatory behavior of our response gets a little worse, but maybe we'll be able to, maybe we'll accept some of that in order to get the disturbance effects down. Okay, so now all we have to do is find out exactly where. I don't have my protractor here, so I'm just gonna say okay, so it turns out that zeta equals 0.707 is a 45-degree line. I'm gonna draw a 45-degree line here. Theta equals 45, zeta equals 0.707. There we go. And so this tells me exactly where do I need to put my desired root locations. Desired root locations. Those are my desired root locations, okay? And so now I'm going to go back and I'm going to use the magnitude criterion. Magnitude criterion, it says 1 plus k p g h equals 0, k p g h equals 1 minus 1. And that means kp. So kp is a scalar, so it's got no direction in but gh is a complex number, so let's just look at the magnitude of that, and the magnitude of that has to be 1, and that just means that kp has to be 1 over the magnitude of gh. And if I use the criterion here, that just tells me that kp, have I fallen off the bottom? I did. Okay. Oh my goodness, I've fallen off the bottom. I apologize for that because I'm not using the right aspect ratio. That's okay. Okay. I'm just going to go ahead and just write down here kp is equal to, so the magnitude of gh, this is the magnitude of s plus 0. This is the magnitude of s plus 5, and then over 20. That's the magnitude of GH. If you go back up and look at what GH is, you'll see that's what it is. And that's what KP is. So what I'm going to do here, I can't believe that. I've messed up this in this particular case. Okay, I'm going to do this over here where you can see it. Okay, KP equals 1 over GH equals magnitude of s plus 0, magnitude of s plus 5, divided by 20. All right, so what is the magnitude of s plus 0? Doggone it. Oh, first let's see what these vectors are. This is the vector s plus 0. This is the vector s plus 5. That's what that vector means. Oh, let me make a vector sign on that. How big is it? Well, I'm going to use this little piece of paper and we'll find out. How big is s plus 0? You know, this is all, I'm just drawing this stuff like this goes to there, so that's about 1, 2, 3. I'm going to call that 3.5. And the reason I'm doing it is, look, those vectors are supposed, like you can use geometry and figure that all out. Those vectors are supposed to be the same size. 3.5, 3.5 over 20. 3.5 times 3.5 over 20 is 0.625. Oh, 6125, sorry, 6125. Okay, so it's 0.6. So if that's how you can design this system, that's fine. Number of poles, number of zeros, I've tried to explain that all out. But now, and the whole point, you know, one of the points is that we can still look at T sub D is still T sub D. We've already done that one. We've already done that one, and we already know if we once we did it, what the transfer function is for T sub D. And if I do T sub D of s equals 0, I just go back and look. It's 1 over 20 kp, which is about 0.08. Okay, so it's still the same. Now, one of the things that, okay, so I'm done with that. We've started with our open loop transfer function. We drew the root locus. We used the magnitude criterion to find out what the gain was. Okay, the last time we did, in the previous part of this video, I just found the gain algebraically. You can do that. It doesn't hurt anything. This will be more powerful later on. And then, in fact, what we're going to do now is I'm going to worry about a little bit more about this stuff over here, Okay, so I'm going to worry a little bit more about this stuff over here, which is I've added a d of s. Now, I see I added a d of s here, and I don't know what I was thinking here. This is supposed to be 20, not 5. That was a typo. I don't even know how I did that. Right? Because I want it to be the same. But in fact, I'm going to do this. I'm going to let you do this one. You can do this one on your own. I'm going to do a little bit different one myself. And here's the one I'm going to do. I'm going to say that there's an input coming in here. Input. And what it's going to be is it's going to be 20. There's a disturbance. We keep that disturbance around, plus. Okay. And then I'm going to do 1 over s times s plus 5. This is x. Now I have to put a sensor on here to see where x is. And if you go and look at the sensor, if you go and look at how sensors work and everything like that, you might see that this is going to be, so I'm going to call this the position Like there might be an analog to digital converter here, blah, 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 stuff like that. And what they might say, this is going to be 10 over S plus 10. This means that omega break frequency, in this case, is equal to 10. That's the break frequency of your sensor. So that's something that you'll hear like, oh, yeah, our sensor has a break frequency of 10. You go like, okay. That's what it means. So now, again, this is the open loop system. This is our second method, second problem. This is our break frequency. And again, you know what? Did somebody say you need to design a controller for this? Okay, that's fine. You got to design the controller, dude. Dudette, whoever you are. Okay, so this again is the open loop system. So just trying to think if I did it. Okay, this is the open loop system. Is it okay I write this down? So let me just do this. This is going to be like, so in this case, this is G of S. And in this case, this is H of S. Okay? So either way, I can still write that the open loop system GH of S is equal to, and you'll see that's the same as down here. GH of S is the same as down here, but here's what GH of S is. 20 times 10 over S plus 5, S plus 10. That's the open loop system. It's got 3 poles and no zeros. That's what we're interested in. And so what we could look at is that we should look at maybe is the number of infinite asymptotes is equal to the number of poles minus the hashtag poles minus hashtag zeros. That's going to be 1, 2, 3 minus 0 is 3. Yay. 3. Oh my goodness, I have to come over here and look at this thing. That's dividing it into 3. It's plus or minus 60 degrees. Plus or minus. I do not have. Okay, so if I try, so I'm just going to draw root locus for this. Okay, root locus. Here goes root locus. Boop. Okay, we're going to just draw root locus. Look how straight my lines are. This is the real part. This is the imaginary part. 1, 2, 3, 4, 5 minus 5. This 6, 7, 8, 9, 10 minus 10. Okay, so this one 1, 2, 3, 4, 5. 5i. 1, 2, 3, 4, 5. 5 minus 5i. See, I tried to compensate. I'm going to slide that one back. This is one of those cases I didn't do a very good job of making everything up, right? So there's 3 asymptotes, and one of the things that I might find out is like, where does the asymptote hit? Sigma asymptote, that's the place that it hits the real axis. It's the sum of the poles minus the sum of the zeros, number of finite poles minus the number of finite zeros. And that's going to be the sum of the poles is, oh, I didn't put them in. Sorry. S equals 0. S equals minus 5. S equals minus 10. Sum of the poles, 0 minus plus sum of the poles, right? That means no minus signs. Minus 5, that's that one. You got to include all the minus signs. Plus minus 10 divided by the number of poles minus the number of zeros is 3. 5. That hits at 5. So now I'm just gonna estimate 60 degrees. Is that good enough for 60 degrees? I don't know. Do you think that's 60 degrees? Let's just estimate. This is how accurate and robust this analysis technique is that I'm just like looking at a 30, 60, 90 degree triangle in my head and trying to draw it, right? Now, somewhere I can also now just start with real axis segments. So real axis segments to the left of odd number poles and zeros. So this is a real axis segment, and that's a real axis segment, right? Those are the real axis segments. Somewhere there's breakaway points. Now, the breakaway points, when they were perfect here, you know what I'm going to do? Let me just draw this in, just for our memory. I'm just going to draw in also. This is what the root locus looked like when we had ignored these higher order dynamics. Now we're going to put them back in and see what happens. And so one of the things, we could go and find out exactly where the breakaway point is. But the breakaway point is the one that's, oh my God, that's like dkds equals 0. Blah, yikes. So let's just make it up. Oh, it's somewhere here. But somewhere that has to come up here and bang in to those asymptotes. There we go. We're done. That's the root locus for this system. There you go. That's the root locus for this system. Now, what we're trying to find using this root locus is we want to know what kind of gain can we use. If I had again, if I just had a graph paper and a protractor, I'd be okay. But let's just put there's theta equals 45 degrees. That's zeta equals 0.707. That means that I'm going to put my desired root locations somewhere like this. That's where the desired root location is. And so for that desired root location, I'm going to write this. This is s plus 0. That's that vector. This is s plus 5. And then this is this vector, s plus 10. I like to usually write these on top, but that was going to get in the way there, right? And so now, in order to find what gain should I use to make that system go to that spot, I'm going to use the magnitude criterion. Magnitude criterion, which says Kp is equal to 1 over GH, magnitude. And that's going to be s plus 0. How big is that? S plus 5. How big is that? S plus 10. How big is that? Divided by, and I have to put everything on the bottom. That's 200. Right? So now all I have to do is find out how big are these vectors. Well, let's just go see how big these vectors are. So this is vector, this is a s plus 0. This is s plus 5. And this one is s plus 10. All right, so let's see how big is s plus 0. S plus 0 is 1, 2, 2.5. Let's see how big is s plus 5. 1, it's hard to see, 2, 3. Okay, I'm going to call that 3.5. How big is s plus 10? 5, 5, 6, 7, 8. I'm going to call it 8.5. And that tells me that Kp has to equal 0.426. 0.426. So that's not much different than the way we did it the last time. That puts, so where are the closed loop poles now that I've placed them? They are right here. Those two of them. Guess what? There's one of them over here somewhere. A third one. But you know what? This one's out far enough compared to these that I don't have to worry about that dynamics much. It has a little bit of effect, but not much. Okay? And so I still have to go back and look at let's see. What is the closed loop transfer function T of S is equal to the output over the input. The closed loop transfer function, I never even drew. I should have. I've been negligent here. I should have drawn Kp, that. Okay, so like that doesn't add anything. Like you already knew this part, right? So I didn't really need to add that. This is XD. Like I'm doing the close. The reason I didn't add it is because what's important is the open loop system. The reason the open loop system is so powerful is because in the open loop system, I can see what all the roots are. In the closed loop system, I don't even know where the roots are. Let me look at what the closed loop system looks like here. It is Kp, numerator of G, times the denominator of H, divided by the denominator of G, S squared plus 5S, times the denominator of H, S plus 10, plus the numerator of G, Kp, times 20, times the numerator of H. That's numerator of G, denominator of G, denominator of H, numerator of G times the numerator of H, right? Numerator of H. I did that a little bit wrong. And I'm going to go ahead and write that all out. Let's just go ahead and figure it out. This is 20 kps plus 200 kp divided by, let's see, this is going to be s cubed plus s cubed plus 10s squared plus 5s squared plus 50s plus kp times 20. Okay, I'm going to write the whole thing out again just because it makes it clear. Plus 200 kp divided by, this is s cubed plus 15s squared plus 50s plus 20 kp. Okay, where are the roots of this characteristic equation? You can go MATLAB and find those roots. For a cubic, you can find the roots, but guess what? I already know where they are. Look, 1, 2, 3. That's where I designed them to be. That's where they are. That's where the roots of that characteristic equation are. And the best news about this is that T of S equals 0 is equal to 1. Yay, again. Yay, again. And then if I wanted to know what T sub D is, I'm going to use the transfer function here. I'm not sure how to designate that. Let's just do it in our heads. We're going to follow that through. This is the numerator of G, 1, times the denominator of H, S plus 10. Numerator of G times the denominator of H, plus, divided by the denominator of G, S, times S plus 5. Oh, you know what? Okay, I'll do it. Okay, it's the denominator of G times the denominator of H plus the numerator of G, 20 kp times the numerator of H, which is 10. And, I'm not even going to do this. This is S plus 10 over S cubed plus 15S squared plus 50s plus 20 kp. Duh. By the way, just so you know, always the same characteristic equation. Yay. Okay? That's always the same one. And now if I want to know what T sub D, oh, curse me, Red Baron. I fell off the bottom of the page. I apologize to you guys. Look. So let's do it again. So numerator of G times the denominator. And you don't even have to do the bottom of it because you already did it. It's the same. And if I want to know what T of D of S equals 0 is, that's just going to be, oops, there's one more. I missed something here, 10. I missed a 10 there too. It's okay. I missed some. It's okay. It's going to be 10 over 200 kp. And since kp is about the same, it's about the same error, So it doesn't change it. What does it change? So what it changes is that when we neglected those dynamics, we were willing to go ahead and put our roots higher and higher. If you go and look at the solution to that homework assignment, we're willing to put the roots higher and higher in order to get rid of the disturbances. But guess what happens now? As we put those roots higher and higher now, oh my goodness, you know, now we're getting into some dangerous territory. Okay? All right, so that's the second part of it. So now let's go ahead and let me go ahead and finish this problem how I would. So when I gave this problem out, I expected that you could just do it algebraically the way I first did it during this video. But now that we've had more functions with it, it's like, okay, for the system shown, design a control system to produce a response. Okay, boop, 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 boop. So less than 5%, that tells us zeta equals 0.707. That's from the charts. Okay, this is Kp, x desired, x minus. All right, there's our control system. Now, I think I'll just do it with the root locus method here. I'm just going to do it with a root locus method here. 1, 2, 3, 4, 5. Right? 5i. Do I have to do the bottom one? Yeah, I could. Okay, and since I already know how root loci work, here's s equals 0, here's s equals minus 5, and I know that the sigma asymptotes is equal to the sum of the poles minus the sum of the zeros over number of poles minus number of zeros. That's going to be 2.5. So here's the breakaway point, sigma asymptotes. I know that the asymptotes are plus and minus 90 degrees, so I've got to write those in. So here's the root locus, right? And then I'm going to say, oh, you know, zeta equals 0.707. This is going to be 2.5. 2.5. Okay, so here's a 45-degree line. 45. These are my desired root locations. So for this root, I would like to draw this is going to be s plus 5, s plus 0. And all I have to do now is find out that Kp is equal to 1 over magnitude of GH, which is equal to, how big is s plus 0? How big is s plus 5 divided by 20? S plus 0, I don't know. I'm running out of like s plus 0 papers here. That's s plus 0. Oh, they're both the same size. So let's see how big are they. Oh, this one says, that one says 3. That one says, see, I didn't make them exactly square. So I'm still just going to maintain, I don't care what you say. This is still 3.5, 3.5. Still, this is 0.6125. Check. Okay, done. And then when I'm coming to grade this thing, I just go like, oh, grading it. Oh, yeah, baby, good job. 100%. Not overshoot. Okay? Okay.